Aniruddhan, this diodes etc. I've seen. P, N, although junction cannot be seen, but we can feel it.
Yes.
BJT, I can see 3 legs coming out from the device.
That is true. Yes.
But how is it inside is not very clear. Same with MOSFET.
Correct. If you look at the device, there will just be 3 legs
Correct.
coming out.
Correct.
You can't. In fact, unless you know a MOSFET and a BJT, each one will have 3
Yeah.
legs. You won't know what it
Yeah.
is, right?
So, can you give some idea how the structure looks like? This
Okay.
PNP
Correct.
junction, how is it actually made?
Okay. So in fact, we also said no, you can't just take 2 PN junctions and connect them
Yes,
together
yes,
to
yes.
make the
Yes,
transistor BJT.
Yes.
So we should give them an idea of what
Yeah.
the device looks like.
Yeah.
No? Okay, let's do it.
Some drawing will help.
Some
to-
drawing will help them
Yeah.
understand. Okay. So maybe what we'll do, see, it is a 3-dimensional device. So can you suggest how we will?
Maybe some, see if it is something like this, you can, from the top if I look,
Correct.
it's flat and a square shape I'll see.
Correct.
From the side if I look, there is another shape.
Okay.
Or if I cut like this,
Correct. Correct.
there is another view.
That is true. Correct.
Although I don't want to do that.
You don't cut your phone. Correct.
But if you do this, I think then we can get an engineer's view of
That is true.
what it is.
In fact, we used to learn something called engineering drawing. Right?
Yes, yes.
So nowadays, it's taught in a very abridged fashion.
Correct, correct.
But
Many tools are there.
many
so-
tools are there to understand. Maybe we'll do that. So
Yeah.
we'll maybe take 2 views. We will do the top view
And cross section.
and the cross-sectional view. So
Yeah.
we'll cut the device vertically in half and look
Yeah.
at what it looks like. Okay, let's do those 2. So we'll start with the BJT.
Yeah.
Okay. So this is our so collector, emitter, and base.
Yeah.
So this is your MP and BJT. So what we said was, in the case of the BJT, NP and BJT, the emitter is emitting electrons.
Correct.
We want all of it to go into the collector so that beta is very large.
Yeah.
Right?
Yeah.
So that much we know. And we don't want to add any side paths for current to flow through.
Yeah.
Right? So that is kind of the way we want to build the device. Now because of that, so emitter is emitting electrons. I'm imagining if I wanted to build such a device, it is going to be emitting electrons. I want to collect them, right? So I'm imagining I have a small plate filled with holes, right? I fill it up with water, which is standing for electrons. All those electrons are pouring out through the holes. I want to collect them. I need to put it inside a big tub or something,
Correct,
or a bigger
correct.
vessel.
Correct.
Right. So I suspect
You want
that
to collect from all the sides.
I want to collect from all the sides.
Okay.
So I'm thinking that the collector should look like something that is all around, right? And in fact, a real BJT, a good BJT, very often is built like that. So shall we look at the top view?
Top view. Yeah.
Top view. So now that I'm now imagining, look at my analogy, the top view of that will only be the plate plus maybe the base plus the, right?
Yeah.
Something like that.
Yeah.
So the top view will look like this. So I'll show the top view here. And the side view here. Okay. So
Or cross section.
cross-sectional view, correct. Cross-sectional side view, right? So now the top view, I said the emitter is there.
Yeah.
This is my emitter. And the emitter is emitting electrons. Now there is a junction, emitter to base junction. And the current should eventually flow into the collector.
Sorry.
So, which means the base should be around the emitter, right? So that means that I need to have a base region. And then outside area is the collector region, right? Something like that I need to have. I'm just building a very crude model.
Yeah.
Something like this. This is my top view. This is my collector.
Okay.
Okay. And the way I am imagining, so the water is dropping because of gravity, no, pouring through those holes. So in other words, the emitter electronic current, no, is going like this. The actual current is flowing the reverse way, right? So this is electrons. Actual current is flowing out, like this. So which means the current is actually going from the circuit. There is a wire connecting to this point. It is going into the page. That is flowing through the base very quickly. It is not coming out of the base node, the wire. The base wire, so if I were to show some wires, no, the emitter wire may be like this. I'll show the base wire like this and the collector wire like this, right? So this is my emitter current flowing, flowing out of the device, right? I'll make a contact here to the semiconductor and take out emitter current. I want no base current. So if I make a contact, I can only make a contact out here. I cannot make a contact under the emitter, right? That water should be going down into the collector. So no current, no base current. Very small, right? That will happen when all of the current flowing, all of the electrons flowing from the emitter to the base will go to the collector, right? So that should be kind of, maybe I'll show it on this side. This is my collector,
okay,
right? So it should
and the cross sectional view.
Cross sectional view, shall we show here?
Sideways will be better.
I am just going to turn this around and cut it, no? So then you will basically see a tub. So I will show it here. You will basically see a tub for the emitter. And then around that the base tub will be there.
Okay.
Base tub. And now the whole thing will be collected by the collector tub. The collector tub. Okay, and I'll have these 3 wires here also.
Okay.
So I'll show like this. I'll have 3 wires. 1 wire like this, 1 wire like this, and 1 wire. These are the 3 wires that we will see, right? So emitter current is flowing out. Base current is flowing in. Collector current is flowing in.
Okay, I think this is quite clear.
This is quite clear, no?
Now I understood from where all this,
Correct.
3 legs are coming out.
Correct.
Okay.
So if I were to, in fact, show where the current would come, no? So the collector current would flow like this, right? And then you want it to flow directly out through the emitter. You don't want it to get diverted like this. That is what we are saying. So that base current is small. So in fact, the way you would do that is by making this very thin. That base width, no, will be very thin, so that as much current as possible goes into the emitter.
Understood.
Instead of coming out through the base contact.
Oh, this is nice.
Good. So I think now we got a good idea of what the BJT would look like. Now we'll look at the MOSFET.
MOSFET. Yeah.
Sure. So now the MOSFET has this gate, drain and source. Now unlike the BJT is actually a vertical device. You can see that the current is flowing vertically. Inside the device, I'll remove these 2. Inside the device, the current is actually flowing like this.
Correct.
Sorry, it should not come out below the collector, right? The current is flowing like this, right? Inside the device, vertical. Whereas MOSFETs, most commonly horizontal, right? So we'll first look at the top view again. So what you need is a gate with a oxide, right? But we won't be able to see it. We'll have the metal gate or the polysilicon gate. Below that will be gate oxide, and then below that will be the device, source and drain. So I'll draw it like this. So I'm going to exaggerate so that we understand the gate. I'm going to make the gate very wide. So that I'm going to exaggerate it. Modern MOSFETs, the gate will not be so long.
Yeah.
Right? So now let us say this is the source and this is the drain. Right? So maybe I'll make it symmetric.
So the gate is actually on top of this device.
Gate is actually on top of the source and drain.
But in the top view, I cannot see it.
You cannot see it. Correct. So this would be the gate.
Yeah.
And below it is the oxide and then source and drain. Right? And actual current is flowing from the drain to the source.
Yeah.
Under the gate.
Correct.
And this is what you pointed out, no? Right at the beginning. You said there is no gate current.
Yeah.
And you said that you some channel or something is there, and you said that the electric field is allowing the transistor to turn on and allow current to flow.
Correct.
So that is correct.
So the cross-sectional view is...
Yeah. So cross-sectional view we'll draw. Just two things. For the BJT, it's an exponential device.
Yeah.
And the only parameter we had in the equation was the saturation current. And the saturation current is a function of the base emitter junction area. Cross-sectional area.
Yeah.
In the case of the MOSFET, we had W and L.
Yeah.
So we need to mark that here.
Correct.
Right? So shall I mark that here?
Correct.
So it turns out the channel is under the gate, under the oxide. So this would be the length of the device. Also the length of the channel. And the width of the device would be this vertical dimension in the top view. Okay. So remember we said W and L, W over L. That refers to these two. This is the length of the channel. This is the width of the transistor. And you can choose W and L to get more current, less current, things like that.
Correct. Okay.
Correct. Now what we can do, we can take the device, turn it around, slice it.
Yeah.
We'll do that. Now what will happen? I will now need to see the source and drain, no?
Correct.
So the source and drain, I'm going to cut it somewhere here. Now what will happen? The source and drain. So now this is some dimension, no? Some, we'll call this some D1 or something. And this is also D1, let us say symmetric, no? That will be this dimension here, D1. And I have the length of the channel. Now cross section will show the oxide.
Yeah.
Right? So this is my source, this is my drain. We also said this is D1. And this is the length of the channel. So I'm going to show the oxide like this.
Yeah.
And this is L. And now on top of that I have the metal, polysilicon, whatever it is. And this is my gate. And here I can have my source connection and my drain connection. And this is the depth, and I don't know what that is, maybe I'll call it T. You cannot see that in the top view, right? And same way, the minute you do cross section, you cannot see the width of the device also, because it's a horizontal dimension into the paper, we can't see it. Right?
So the source and drain are formed using that doping we mentioned.
Doping, correct. Correct.
Nice.
So I think we have all of them. So if I were to imagine some perspective view, maybe into the paper, no, like this, if you were to draw something like that, that will show the width dimension if you want. But actually, technically, cross-sectional view, you won't have that.
In the cross-sectional view, we will not see.
So I will just remove those, but just to give students an idea.
Correct.
Right. So I think the mu n will correspond to the mobility of the electrons in the source and drain regions. Then source and drain regions and in the channel. Then the what is Cox? Cox is the oxide. Now that is important here. Cox would be, so you have this oxide
insulator
here.
There,
so this is the insulator here. This is your insulator. That is why your gate current is 0. Now the capacitance of that will be Cox.
Okay.
Right. So that will depend on the area of the gate. So now the area of the gate is this on the device.
Yeah.
W times L. So the total capacitance will be Cox times W times L. That is why your Cox is the capacitance per unit area, right? To do that, you need to know. So this looks like a parallel plate capacitor, no?
Correct.
So this is one metal. You'll have some channel here. You can find out all of that. That depends on the thickness.
Yeah.
It depends on the thickness, on the relative permittivity of the oxide, etc.
Yes.
But I mean, so that is Tox here. So we can keep going, right? Again, for the BJT, we only went to this level. We'll stop here for the MOSFET also. So I hope the students would have got a good idea.
Some good idea
feel
of the
for
structure.
This.
Anyway, more if you need, we can read
Correct.
standard textbooks.
Correct.